I'll present a semantics for the PTQ fragment that models the fragment through the use of just one single basic type of object, and that's also why I call this semantics a single type semantics. Now, the possibility of providing such a single type semantics for natural language has first been proposed by Barbara Partee in a 2006 paper on the question of whether we need two basic types. In this paper, Partee conjectures negatively that Richard Montague's distinction between entities and propositions, as you find it, for example, in the EFL paper, is not necessary for the construction of a rich semantic ontology. And she conjectures positively that instead the PTQ fragment can be modeled through the use of just one single basic type. And in what follows, I'll refer to the conjunction of these two claims as the single type conjecture. The essence of this conjecture is then that whereas Montague semantics assumes at least two basic types of objects, say entities and functions from indices to truth values or propositions, from which all others are constructed as objects of a derived type, single type semantics assumes just one single basic type, I'll here call it O for the time being, and assumes that this type is semantically neutral between entities and propositions, such that from this type, all other types of objects can be obtained via the standard type forming rules. Now, in virtue of the neutrality of the type O between entities and propositions, a single type semantics assigns the single basic type O to both proper names and sentences and complement phrases. Also, in line with our assumptions, it will assign the minimally complex type OO to both common nouns and to complementizers and sentence adverbs, and it will assign to expressions from all other syntactic categories the results of replacing the types E and ST by just our single basic type O. And the objective of my talk for today will be to provide formal support for Partee's conjecture, and to do this, I'll develop a single type semantics for the PTQ fragment. Now, in this way, I hope to answer a number of questions about the type system and the semantic ontology of natural language. These include the question of what happens if we replace our two types E and ST by a single basic type, whether this is possible at all, and if yes, under what conditions, what a suitable interpretive domain for the single basic type O will look like, and what its semantic properties are. Maybe philosophically more interesting questions are the questions of what effects this change of type system will have on the ability of our semantics to model natural language, how such change will influence our understanding of the relations between different types of objects, and whether in the end this will make Montague's type system dispensable. Now, to answer all of these questions, I'll proceed as follows. In the last couple of slides, I've already presented you Partee's conjecture about the possibility of such a single type semantics. To motivate this conjecture, I'll next present different kinds of support for the conjecture. This support will include formal support, which demonstrates the existence of single-type models. But we'll soon see that the provision of this formal support faces a number of challenges. In the third part of my talk, I'll present some of those challenges for the provision of a single-type semantics. In the fourth part, I'll identify a strategy towards the solution of these challenges. In the fifth part, I'll use the solution strategy to provide a single type semantics for the PTQ fragment, and I'll finish by trying to answer the guiding questions from my previous slide. Now let's start with some empirical motivations for Partee's conjecture. The conjecture is in fact motivated by a very analogous claim on the level of natural language syntax, and in particular in his monograph on the origins of complex language from 1999, Andrew Carstey-McCarthy conjectures that the syntactic distinction between noun phrases and sentences is not necessary for the generation of complex modern languages, and that instead all syntactic categories that we use today can be obtained from just our use of one single basic type. So again, the essence of this claim is that whereas most theories of traditional syntax assume at least two basic categories, say for noun phrases and sentences, Karsten-McCarthy's single category syntax assumes only one basic category, which Karsten-McCarthy labels X, and of which he assumes that it's neutral between noun phrases and sentences. And again, from this one basic category X, all other categories are obtained just via the standard category forming rules. Now, Karsten-McCarthy supports this hypothesis with reference to the observation that the distinction between noun phrases and sentences is an evolutionarily contingent property of modern grammar that leaves open the possibility of an alternative single category syntax. Now, because of the close relation between syntactic categories and semantic types, we could try to provide a semantic analogon of Karsten-McCarthy's argument and argue thus for the need or the possibility of such a single type semantics. Now, of course, these are very, very strong claims, and I think that in fact there's much more interesting support for Porty's conjecture. And this support lies in the identification of phenomena which can be modeled in a single type semantics, but which defy accommodation in traditional monouse semantics. One such phenomenon would be the use of many verbs which select a complement that can be realized either as a noun phrase or a complement phrase. One of such verbs is prove, for example. So we can use the sentence, Tom proved the hypothesis, noun phrase, or Tom proved that the hypothesis was correct. And similarly, we can have the sentences, Pat remembered the appointment, and Pat remembered that it was important to be on time. Now recall that in traditional monouse semantics, we treat the NP and the CP as an expression of the type E and the type ST respectively. And because further traditional monouse semantics assumes that each syntactic category is associated with exactly one semantic types, we will in this system be able to model at most one of the elements from these pairs of sentences. And also, because traditional monouse semantics restricts coordination to expressions of the same semantic category, we will in this system not be able to model the result of coordinating a noun phrase and a complement phrase, for example, as in the sentence, Pat remembered the appointment and that it was important to be on time. Another kind of phenomenon then, which also can't be modeled in monouse semantics, is the use of proper names to assert a contextually salient proposition about their type E reference. For example, if I use the name Barbara Partee as a woman is entering the room, my particular utterance of the name Barbara Partee in this context can be interpreted as the sentence, Barbara Partee is the woman entering the room, for example. And in virtue of this sentence type interpretation of the name in this context, we can evaluate the truth or falsity of my utterance of the name Barbara Partee in this context. In particular, we can say that Barbara Partee is here true if the woman entering the room is in fact Barbara Partee, and it's false otherwise. And again, also because of the truth and falsity conditions that we can then claim of proper names, we can say that my utterance of the name Barbara Partee in this context would be equivalent to the name Barbara Partee is entering the room. And this observation of a semantic equivalence of some sort of semantic relations between proper names and sentences or between proper names and complement phrases is further supported by the fact that the result of coordinating some of the complements of the verbs from the previous slides engenders some sort of feeling of redundancy. So for example, once we have learned that Thomas proved the hypothesis, learning that Thomas also proved that the hypothesis was correct doesn't yield us any new information. And these are all examples that can be regarded as an illustration, if you like, of the advantages of such a single type semantics. But you'll probably already have thought that there is still one problem, namely that all of these phenomena can also be accommodated simply in a flexible monogrammar with an E to ST type shifting function. And in fact, since type shifting is an already existing mechanism that will in this case enable an easy accommodation of all of these facts, the empirical support for Partey's conjecture will only exert very little confirmatory force. Stronger support for the conjecture will then come from methodological considerations. These will especially include considerations of the unification of Montague's semantic ontology and of the identification of representational relations between different types of objects. With respect to the first of these facts, observe that by replacing Montague's types E and ST by just one single basic type of object, we'll be able to achieve a complete unification of the semantic ontology, such that our new basic type O will be able to bootstrap all PTQ reference without the use of a second or a third basic type. With respect to the second of these points, we can observe that by identifying just one single basic type, and by shifting all Montagovian objects to constructions out of the single basic type, we would be able to expect that our single type semantics extends the representational relations from flexible Montague semantics. For example, in flexible Montague grammar, we have identified, or one standardly identifies representational relations between entities and first and second order properties of entities. Now, depending on a particular single basic type choice, we would expect that we would also be able to identify relations between our single type objects and entities, first and second order properties of entities, etc. And in such a way, we would hope, at least, that our single type semantics would yield insight into the apparatus of types in formal semantics. Now, none of this support, of course, helps us in any way, unless we know that it is in fact possible to construct such single-type models. And to show this, Barbara Partey, in her original 2006 paper, has identified just one such single basic type, which she has described as properties of Kratzer-style situations. And she has provided an O-based semantics for a fragment of English. Now, in her semantics interprets the personal pronoun you as the property of being a minimal situation containing you. It interprets the indefinite a snake as the property of being a snake-containing situation. It interprets the transitive verb see as a function from two situation properties, P1 and P2, to a third property, P3, which holds of a situation S3 if that situation contains two other situations, call them S1 and S2, with the properties P1 and P2 respectively, where something in the first situation sees something in the second situation. And the interpretation of these expressions will then, of course, enable the compositional interpretation of the sentence you see a snake as the property of being a situation in which you see a snake. And in fact, the semantics again provides formal support for Partey's conjecture, but a problem that we encounter here is that Partey's fragment is, of course, very, very small. In fact, the 4 words that you see here is all that there is to the fragment that she provides in her very short paper. Also, because the presentation of Partey's single-type semantics is informal, it doesn't provide compelling support for her conjecture. And the objective of the rest of my talk today will be to try to formalize and extend Barbara Partey's model. Now, contrary to what Partey seems to suggest, the provision of this formal support is not very straightforward, and in fact it faces a number of challenges. These challenges include the fact that existing single-type semantics turn out to be unsuitable for our purposes, that straightforward, simple adaptations of these semantics disable an easy definition of truth, equivalence, and many other semantic notions, and that successful single-type semantics, which do serve our purposes, require the introduction of many new non-logical constants and employ a very, very strict distinction between the object and the meta level of this theory. And in the next couple of slides, I'm going to discuss some of these challenges in turn in some more detail so you see where they really lie. Let's start by considering the first of these challenges, that is, the unsuitability of existing single-type semantics for our purposes. And examples of such semantics are models of Church's untyped lambda calculus or models of Henkin's theory of propositional types. Now, arguably, the untyped lambda calculus has a single basic type which we can identify with a universal type, and the assumption of this type in fact supports Partey's conjecture. The problem is that because in the untyped lambda calculus we do not make a distinction between functions and arguments, we can essentially apply anything to anything, and as a result we will no longer be able to explain the well-formedness of natural language expressions. Also, because models of the untyped lambda calculus are quite different from models of Montague's intension logic or from models of Galen's logic type 2, we refrain from using these models as our single-type semantics. A single-type semantics, or a second alternative that is already much closer to home, would be the models of Henkin's theory of propositional types. In this theory, we have just one single basic type, which is the Boolean type for truth value. So this seems to be nicely in line with what we are used to. The problem is that typically, of course, we have fewer Boolean values than entities or propositions, such that there doesn't exist an injective function from the domain of entities and propositions to a 2 or 3 member set of truth values. And as a result, we seem to be unable to provide a principled representation of basic Montagovian objects in our basic single-type objects. One possible solution to this problem would be to simply replace the type T in Henkin's theory of propositional type by another type, for example, by the primitive type O from the first couple of slides in my talk. But a problem that we then encounter again is that unless we identify the type O with the truth value type T, the standard truth functional connectives and quantifiers will no longer be available. Also, unless we assume that our type O is some sort of construction to the truth value type T, we will not be able to provide an easy truth condition for sentences, and also because it seems that it will be quite difficult to identify equivalence relations between proper names and sentences, we seem to be unable to model the empirical support for Partey's conjecture that I've cited a little bit ago. The solution to all of these problems that I'll adopt here in my talk will be to replace the single basic type T from Henkin's theory of propositional types by the type for functions from indices to truth values, such that as a result, our single type logic will be an ST-based subsystem of Galen's logic type 2. Now, my choice of the type ST as the single basic type of my logic is motivated by the fact that this type has many desirable semantic properties. First of all, the type ST is very close to Partey's original single type choice, which, just as a reminder, were extensional properties of situations. Second of all, because it is a construction to the truth value type T, we expect that the type ST will enable the truth evaluation of proper names and sentences. And also because the relative size of its domain, we expect that the type ST will enable the specification of an injective function from the domains of entities and propositions to objects of our new single basic type. And in particular, for the purposes of this talk, I'll adopt such a function that sends propositions to themselves and that sends entities to the set of indices in which these entities exist. As a result, we will then be able to obtain the familiar truth conditions for sentences, and we will also be able to evaluate the truth and falsity of proper names via the truth and false, via the existence or non-existence of the type E referent of the name in the relevant index. And as a result, we will then be able to define the equivalence of proper names and sentences via the truth or falsity of the names and sentences in the same indices. Now, let me briefly make two remarks here. One is that in order to be able to use this representational strategy, we still need to use a multi-type meta-theory for our single-type semantics with distinct types A, S, and T. And this is due to the fact that you've seen here that our description of the representations, for example, of entities in the type ST will still explicitly refer to indices, entities, and truth values. The second point that's interesting is that also because our representational strategy uses the existence predicate exists, if we then want to be able to have the standard behavior for negation, we need to be able to interpret our types ST in a partial logic. So in fact, we'll not adopt Tie2, but a partial version of Galen's logic Tie2 as our meta-theory. And on this basis of this very rough strategy, we will now be able to provide a single type semantics for the PTQ fragment. To do so, I'll use Montague's method of indirect interpretation that proceeds via the compositional translation of the PTQ fragment into the language of our single type logic. And to enable this interpretation, we then first have to develop the language and models of our single type logic. And subsequently, we'll have to provide a set of translation rules that send expressions from the PTQ fragment to terms of a single type logic. And in the next couple of slides, I'll first start by presenting you the single type logic. In the previous section, I've already mentioned that we'll assume that this logic will be a subsystem of a partial version of Galen's logic Tie2 that only has one single basic type, namely the type for functions from indices to truth values. And our description of the type ST as the basic type of this logic is motivated by the fact that the Tie2 types S and T do not qualify as single type types, such that as a result the type ST cannot be obtained from lower rank types through our single type forming rules. From the basic type ST, complex types can then be obtained via the rule that the type for functions from n+1 tuples of objects of the types alpha 1 through alpha n and T, S, to the type T will themselves be a type. As a result, the set of single type types will then contain the propositional type ST, the type for functions from propositions to propositions ST, ST, the type for functions from ordered pairs of propositions to propositions, and the type for functions from propositions to propositions, and of course, many, many others. The terms of our single type logic are almost standardly defined, but remember that because the standard truth functional connectives and quantifiers are not available in our single type logic, we need to assume that the set of non-logical constants includes suitably typed stand-ins for those standard connectives and quantifiers, which you see here on the left-hand side. And from these basic terms, complex terms will then be obtained inductively through the usual rules of functional application lambda abstraction and through the single type stand-in of logical implication. In our single type logic, frames and models also will have almost the usual definitions. However, remember that because we work now in a subsystem of partial Tie2, we'll associate our single type domains with constructions to the three-member set of truth values, true, false, and neither. Because we've identified our basic type, our single basic type, with the type ST, we will now be able to evaluate the truth and falsity of basic single type terms. However, because our single type logic doesn't have designated types for indices and truth values, this evaluation must proceed in models of the meta-theory Tie2. As a result, we can then say that a basic single type term A is true at an index W in a single type model M, exactly if A is true at W in the embedding model M superscript 2 of the meta-theory, and the inverse then holds for falsity. And also entailment for very similar reason needs to be defined in the meta-theory, which is 3-typed. This suffices, I think, for the time being, for the presentation of this single type logic. And in fact, we've now already seen a general class of languages and models of a single type logic. To present a single type semantics for the PTQ fragment, the only thing that we now have to do is to identify a designated language interpretation function and frames of the single type logic, and to specify the translation relation between expressions of the PTQ fragment and terms in our designated single type language. Now let's start by presenting this language, the specific language, and we assume that this language consists of single type stand-ins for the familiar truth functional connectives and quantifiers. For example, here you see the stand-in for the universal and the existential quantifier, logical implication, the stand-in for identity, etc. And also we assume, of course, that this language contains the single type translations of certain PTQ words, like the translations John, Mary, and Bill of the proper names John, Mary, and Bill. We assume certain conventions for variables and make the usual assumptions with respect to the size of the designated frame and the designated interpretation function. We identify logical form with a component of syntactic representation which is interpreted in our single type models, and we assume further that logical forms are translated into single type terms via Klein and Sachs method of type-driven translation. The base rule of type-driven translation will then assign the proper names John, Mary, and Bill to the non-logical propositional constants, or ST constants, John, Mary, and Bill. It will assign the common nouns man, woman, and unicorn to the type ST constants man, woman, and unicorn. And it will assign to all other PTQ words suitably typed variants of terms that look suspiciously like the original Montegovian translations, modulo a couple of changes. To see that the translations do the job they're supposed to do, I'm next going to translate a couple of example sentences from Montague's PTQ paper, and I'm going to start by translating the very simple sentence, Bill walks. Now we've already seen on the previous slide that the base rule of type-driven translation will translate Bill as the propositional constant Bill, and will also translate the intransitive verb walks as the type ST constant walks. As a result, walk is then interpreted as a function which applies to propositions, for example, the proposition denoted by Bill, to yield propositions, for example, the proposition denoted by Bill walk. And in a very similar manner, we can then obtain single-type translations of the logical forms of all of the PTQ sentences, like a man walks, every man walks, the man walks, etc. And you see that the results don't look so very strange, but look very much like the original Montegovian translations. There is then just one last problem that we still have, and this is that until now, we've used these translations really only at the level of syntax. By the typing constraints, we then know, for example, that our single-type translation of the sentence Bill walks will be an expression of the type ST, so it will be the characteristic function of some set of indices. But there is nothing until now that ensures that this interpretation in fact respects our strategy. So there is nothing to ensure that the sentence Bill walks is in fact interpreted as the set of indices in which the type E referent of Bill walks. For all that we've seen for now, Bill walks could very well be interpreted as the set of indices in which Mary runs, but this is of course undesirable. And to ensure that this doesn't happen, we introduce a set of non-lexical meaning postulates which constrain the interpretation of these single-type translations. In these meaning postulates, we use the usual constants and variables of the logic type 2 that you find, for example, in Galen. And we assume further on that our designated single-type frame will result from restricting the designated frame of our meta-theory type 2 to constructions out of this single basic type, and will make a very similar assumption with respect to our interpretation function. On this basis, we'll then be able to formulate these meaning postulates that I've just discussed. For example, the first meaning postulates, MP1, defines the single-type stand-ins for bottom as the designator of a constant function from indices to the semantic value of falsum. in line with our strategy for the representation of entities. Our third meaning postulates defines the single type translation of Bill as the designator of a function from indices to the truth value of the proposition Bill exists at those indices, or equivalently as the characteristic function of the set of indices in which Bill exists. The remaining meaning postulates then enable the compositional definition of logical forms of the basic single type as intensional formula. For example, you see here marked in red that we define the single type translation of walk as the designator of a function which sends propositions, here the proposition bold script x, to the set of indices at which the type E referent of bold script x walks, etc. And in this way, we can then compositionally define the single type translation of the sentence Bill walks, for example, as the result of applying the definition of the single type translation of walks to the definition of the single type translations of Bill via a number of lambda conversions. We then arrive at the term lambda I walk Bill I. And this is not only equivalent to the original Monogovian translation of the sentence Bill walks, but that also respects our representation strategy just as originally desired. Now, let me finish my presentation of a single type semantics by saying very quickly something about single type truth. You may already expect by now that the truth and falsity of basic single type logical forms will be obtained via the definitions of these forms' logical single type translations. For example, we can then say that the sentence Bill walks is true at the current index in our single type model, exactly if the definition of the term's translation is true in the embedding model of the meta theory, and this is exactly the case if the type E referent of Bill walks, and it is false if the type E referent of Bill doesn't walk. What's probably much more interesting is that in a very similar way, we will also be able to provide truth conditions for proper names. And this is again due to the fact that in our single type semantics, proper names will be interpreted in the type ST. In particular, because we define the single type translation of Bill through the use of the existence predicate E, we will then be able to say that Bill is true at the current index if Bill in fact exists in that index, and is false otherwise. And because of our particular definition of the single type translation of the predicate exists, we will be able to see that names in fact have the same truth conditions as they're containing simple existential sentences in this particular version of single type semantics. As a result, Bill, which will be true or false, exactly if the sentence Bill exists is true or false at the relevant index, and as a result we have that Bill, in fact, is semantically equivalent to the sentence Bill exists. Now, let's wrap up by trying to answer the original questions that I've asked a couple of slides ago. So, after all I've told you, what happens if we replace the types E and ST by a single basic type? And our answer can now be, well, initially, not much. We're still able to model the PTQ fragment. But to make sure that this modeling, in fact, is semantically principled, we need to use a multi-type meta theory next to our single-type object theory. And as a result, it seems that we can't discard Montague types altogether. Second question, what does a suitable interpretive domain for the single basic type O look like? We've seen that for the purposes of this talk, we've identified single basic type with functions from indices to truth values, but probably any construction to functions from indices to truth values should also be able to do the job. And lastly, what effects does this change of type system have on the ability of our single type semantics to model natural language? There is one positive effect which we've already seen at the very beginning, namely that because we interpret proper names in the same type as sentences, we will now be able to model the propositional interpretations of proper names. However, there's also one drawback, and that is because of our particular representation strategy and the ensuing semantic equivalence between proper names and sentences and proper names and complement phrases, we will no longer be able to explain the ill-formedness of the expressions possibly Bill, Bill exists walks, or that Bill exists walks. There's many other consequences, but I think I'll stop here, and I thank you for your attention.
So thank you very much. This very last consequence reminds me of there was a correspondence between Frege and Husserl, right? And where Husserl attacks Frege on the idea that to identify truth values, the denotations of sentences with individuals, as it were, or terms, and Frege says, I think the question is something of why can we then not say that it's raining +2 = 3 or something, and then Frege says something like that's just an accident of the natural language syntax. So that's a bit like I was waiting for this kind of remark.
It's a very similar consequence.
Yes,
I agree.
And so actually, looking at your, I think however you third slide, right? I think there's the way you presented it. I think.
Are you talking about?
No, sorry. The third slide saying parties conjecture or whatever at the very beginning, right? There, one sees that you're doing two things at a time, which had been done before independently, but not with this kind of three-valued setting. And the first is this identification that I just mentioned. I mean, Frege already said, sentences or proper names, it doesn't matter, right?
Yeah.
Same thing. I mean, denotation.
Truth values are Gegenstände or objects.
Yeah, right. And the other one is the thing, getting rid of S's, as it were, right? And putting them down to the propositions. There's this famous paper by Kaplan, and you mentioned the relation with English as a formal language, where basically the same kind of thing.
You see more or less the same, yeah.
Yeah, but then what you did is you do both at the same time, and then you resort to this meta theory. So that's the way I looked at it, but it's very interesting that it actually works, and this is certainly an idea I've never come across before. But one technical question concerns when you informally presented your strategy, you talked about this representability.
Yeah.
And they said the type enables an injective function f from entities and propositions to type ST objects. How could that be injective?
It's not a function from the union of entities and propositions to single type objects. It's injective from entities.
I see.
I don't actually want the function from the union to be injective, because if this was the case, I couldn't identify a single basic type object that would represent both entities and propositions.
No, I mean, it was obvious that this
injective from each of these Montegovian domains.
It's a union of two injective functions.
Yes, exactly, yes.
Thanks.
Just two very basic questions. I'm looking at the slide that says the language L.
Yeah, let me quickly.
And I think you might have answered that, but so if John or Mary or Bill is of type ST and walks is of type ST, then you combine Bill and walks, and then you get to type ST.
Yes.
And then you should be able to combine Bill walks with walk again, and you get again to type ST. Yeah. Okay.
That's something else that's undesirable that you can't. It's in a way a natural consequence of working with such a single type semantics, because there's something that has to give if you want to make the semantic project work, and this seems to be the something that you have to give. That is in a way a negative consequence for the empirical scope of this project, because you can't model everything that Montague can model or explain.
And just one other very short question, which is very basic again. So it looks like on your truth definition, you should be able to say, so saying unicorns exist should be the same as unicorns are true.
Exactly.
But I think the second one
I don't have a truth predicate in my object language, right? Mm-hmm. So in that respect, I can say unicorns are true because I just don't have a truth predicate in that language. Mm-hmm. If I were to extend my language via truth predicate, this would be another one of those weird consequences, I guess, yeah.
So I'm not sure how much of the empirical support for Partey's conjecture comes from her snippet and comes from you, but so
and none of it comes from her snippet except for the Carsten McCarthy.
Okay, so so then I have this is a question for you. So if a woman enters the room, I can say Barbara Partey, and you're like, correct, that's true. But if somebody comes in to the room and like is looking around, I can say under the table, And you can say, true, that's where my bag is, right? I mean, so I think that there are a lot of things that you can say out of the blue that you can see, but would you say then that prepositional phrases are also of type, this single type, and you get into even more of these problems?
Yes. You could try to go that way and even extend the project to such an extent. I haven't considered this for exactly the reason of the negative consequence. Of course, if you wanted to account for other kinds of ellipses, as the one that you just mentioned, you would seem to be getting more and more of these negative consequences, where in a way you can model more and more, but then you can explain fewer and fewer ill-formed expressions.
And then I have just a related thing. I guess, so English has all these verbs that can take either noun phrases or these CP sort of things.
Yeah.
I guess some of these have that. I think other languages sometimes make it a little bit more explicit to have a nominalizing word in front of some of these things.
Yeah.
I'm not sure that English, whether these are the same things or not, might not be as clear in English as some other languages.
Can you give me an example?
Like maybe Hebrew? Somebody? Like, where's... I'm not... like the fact that a complementary... I can look up papers that will give examples.
I'd be very interested in that, yeah. Thanks.
So to follow up on the Barbara Party question, right? So the example Barbara Party. I'm trying to understand. So does your fragment actually capture this kind of data that you gave? It doesn't, right?
No, it doesn't.
Okay.
I have a stronger single type semantics, which does capture or does accommodate that kind of phenomena. But because it's even logically more complex than the one I presented here today, I thought I'll stick with the simpler one for the time being. I can do it. This fragment or this semantics won't be able to accommodate that case.
And under this, Barbara Party, right, that proposition, right, means Barbara Party exists.
Exactly.
Right.
Yeah, that's completely correct.
So when you said this in support of your of the project, you say that the NPs and CPs sometimes are interchangeable in natural language. But if I say I believe Bill, and I can say I believe that it is raining, but I believe Bill on your account means not that I believe that he's speaking the truth, but that he exists.
Exactly. This is the same problem that was mentioned before. Yeah. This is also one of the reasons why this single type semantics that I've presented you today, I actually call weak single type semantics my dissertation, because it can only capture very few of these semantic equivalences and can't accommodate most of the kind of phenomena that I've mentioned in support of the semantics. I completely agree, yeah. There are ways of making it work, if you like. I can tell you offline later of how this could be done, but...
one of the older motivations for having more flexible types has to do with the possibility of reflexive applications of functions to themselves.
Yes.
And there is some motivation, both conceptual and even empirical, for having something like that. But your system doesn't address this.
No, it doesn't.
It does not allow you to have this kind of reflexive predications that arguably are necessary.
Yes. It's not accommodated in the system as it is. I think it should be fairly easy to do so, but as of now I haven't addressed this, no.
Because that also opens up another way of reducing types. Once you have a reflexive mechanism and a logic for it, it's an alternative way to having something like a single type semantics.
In this case, it would probably make more sense not to stick with church typing, but go to card typing, where you can assign types individually to expressions. I think this would, this is something I haven't done yet, but I think would, you're right, would be a good way of approaching this.
I had a couple of terminological remarks.
Yeah.
So one thing, I think there was some, in the middle of your talk, there was some equivocation going on there between what it means to be single type. I mean, the untyped lambda calculus is not at all a usual suspect, because when you say single type, you mean single basic type.
Exactly.
And that, yeah, right. I mean, then so it's not even a candidate, and that's just a terminological remark. And then the other one, another terminological remark, relates to, maybe it's not quite not just terminological, to type shifting. The way I understand, you said maybe one could try type shifting here, but the way I've always understood type shifting is that it's a very restricted technique. Namely, it has to be either definable, right, if you're Van Bentham or whatever, or it has to be a type shift, or it has to be at least permutation invariant. And none of this applies to the shift from E to ST. So I mean, it's a non-starter. I mean, of course you can call anything a type shift, right? If it just takes you from one type to the other. But since you said the type shifting technique has been around anyway, right? Well, that's not what has been around at all. And
that's not what I'm trying to do, right?
Oh,
I'm just the only reason I'm referring to type shifting is that flexible Montague semantics with such an EST type shift would also be able to accommodate the phenomena that I've cited as empirical support for a single type semantics. But the fact that these kind of phenomena can be accommodated in other ways suggests that this kind of evidence doesn't uniquely support such a single type semantics. I've just used it to weaken this support, as it were.
According to him, it cannot be accommodated.
But
No,
we'll discuss this later. Yes.
It wasn't really what I was saying, right? I think there is no. What I was saying was, I think there is. If you were referring to a shift from E to ST, there is no such shift. That's what I was
you can
saying.
Define a function.
Yeah, right. But that was the terminological remark. You wouldn't call that a type shift because it would just be an arbitrary function. Whereas a type shift is usually understood as something something invariant and injective, or at least those two things, right?
I agree on that.
So this wouldn't, nobody would call this a type shift. I mean, otherwise you could just, of course, you can have functions around, right? But that's certainly not. It's certainly not saying we're using this technique, which usually, actually, most of the time comes with some kind of definability condition on top, right? And it's hopeless, right? EST, it's provably there's provably can be no type shift, whatever a type shift is in the narrower sense.
I agree on that. Yeah.
Well, that was just the terminological one.
We should conclude, but I have one last question. Individual concept, so SE.
Yes.
What would be the type in a single type?
You would have to code it.
Okay.
One thing I've not talked about is how to solve Porty's temperature puzzle in this. It can be done. It can be done. Yes. It can be done. What you have to do is code SE as STE, and then you have 0000 would be then your corresponding single type for individual concepts. And if you then tweak translations, it works.
Thank you.
Thanks.